Good day, everyone. This video contains demonstrations and discussions on practice exercises found on lesson number 2 of unit number 2. The lesson number 2 talks about the content of unit number 2, which is on the rational exponents. In the previous lesson, we talked about the reviews of laws of exponents, which are actually represented first by the integral exponents. In lesson number 2, as for this video, we will talk about the fractional exponents. Fractions are still part of the rational numbers, and it's still possible for our exponentiation or exponential notations to have fractional exponents. So how do we deal with fractional exponents? We are going to talk about the practice exercises found in your modules as part of our discussion. Let me share to you first the material of lesson number 2. At the bottom here, I already have added the material here. So let me just click this material. This material was already presented to you, and of course, the contents were already discussed. So we are not going to talk about how the contents were discussed, how the contents were delivered, but we are going to talk about the practice exercise immediately. As for lesson number 2, we only have two different practice exercises. This video will talk about practice exercise A. So this one, we have three numbers with expressions containing fractional exponents. And we are asked to simplify them. As to how, we are going to use the additional law of exponent attached in this module. So I'm going to share to you the area to where we could just actually scribble and add some very important notes as to how. Okay. Now, this simplifying these expressions with fractional exponents involved a considered sixth law of exponent. In the previous laws of exponents, we have five. We have the multiplication law, the division law, the law of zero exponents, we have the power rule or the power law, and we have the law of negative exponents. We could actually consider this one as the next law of exponent, which will actually be concerned on fractional exponent. We can consider this as transformation law, or simply you can name this as law of fractional exponents. It states, before we go to those items, it states that if you have an expression, let's say uh, x to the power of m over n. Okay, so as you can see, the exponent is a form of a fraction where m is the numerator and n is denominator. Well, let us not use m to the power of n. Let's use another letter so that you could actually verify it better. M to the power of k. This expression can be transformed into an expression with radical expressions. Radical expressions are those expressions with roots, just like square roots, cube roots, and any nth root. So this could be transformed into a radical expression where your base becomes here, becomes your radicand here. This is called radicand. Discussions on this will be given in your will be explained better when you reach unit number 3. But of course, in the meantime, this is called a radicand. Okay, radicand. The base will become the radicand. The numerator of your exponent will become the exponent of the radicand, and the denominator of the fractional exponent will become your index. Okay, will become your index. So when you try to convert it into an expression with radical expressions, you can just simply get its value or solve for its value. Let us try. Okay, so we have here items A number 1, of number 2, we have here number 3. Let me align this better. And this one here. Let's start with number 1. Number 1 is 49 to the power of 1/2. Okay. So we could just simply solve this value by using the sixth law of exponent. Again, you can call it transformation law. You can call it law of fractional exponent. Either way, the point here is from an expression with fractional exponent, we can transform it into a radical expression to simplify or to give the answer. As to how, again, this will be converted into, this will be converted into a root of 49. Your base becomes your radicand. The enumerator of the exponent becomes your exponent of the radicand, and your denominator of the exponent will become your index. Further, this is actually equal to any number raised to the power of 1 is the number itself. Okay, and then 2 here means square root. Uh, there is a concept that if it's a square root, it's okay not to place any index because this index means it's already in square root form. As for this, we have square root of 49. So we can get the value right now because 49 is a perfect square. 49 is 7 times 7 or 7 squared. In short, the answer for this is 7. Okay. Using the concept of this law of exponent and the simple um, simplifying of expression, the answer is 7. As for number 2, okay, let me move number 2 here because this might need um, better uh, this demonstration. Yeah. Okay. As for number 2, 9 to the power of 2/3. Again, let's convert it into an expression with radical expression. With you have here 9, and then you have here the exponent. You have 2, and then you have here 3. In short, this is now a cube root of 9 squared. There are two different possible ways here that you could actually what do you call that? You could actually simplify it. But of course, you could just simply convert it to 9 squared. So this answer of yours will be cube root of 9 squared is 81. Okay? Cube root of 81. Now, as of the moment, we will accept the answer of the cube root of 81. As to why I said we will accept right now the cube root of 81 is the fact that we can still simplify this. We can simplify this expression when we are when we reach unit number 3. So let us not talk about how to simplify first as of this moment. We can simplify this expression when we reach unit number 3. So please take note of that because I'm going to probably give this example still when we reach unit number 3. Okay, so this for the meantime, that is cube root of 81 as of the moment. We will accept that as our final answer. As for number 3, the final item, let us have here the 81 to the power of 3/4. Again, converting it to an expression with radical notation, you have here index of 81, and then we have 81 cube, and you have here fourth root. The fourth root of 81 cube. Now, of course, we will try our best to simplify this. As for 81 cube, that is very big. You might take uh, plenty of problems later on as to simplify that. But for the time being, let us take 81 cube. 81, the product of 81 cube is equal to 81 times 81 times 81, meaning there are three 81s multiplied to each other. This is actually equal to the fourth root of, if you may use your calculators for this, 531,441. Okay, it's so big. Now, sir, how do we simplify that? It's very big. I cannot even memorize, sir, square root until 20. I mean, perfect square until 20. I even have problems in familiarizing the power, the cubes of numbers from 1 to 20. How much more with the fourth root and this big? You this problem this is the problem right now because we already simplified the radicand as 81 cube. But actually, we can also create another step to this. Okay, if this seems very impossible to be solved using this expression, we can use the concept that 81 to the power of, okay, I'm going to write it here. 81 to the power of 3 fourths may be rewritten as 81 raised to the power of 1 fourth times raised to the power of 3. We are doing the reverse operation of the power rule, wherein if we're going to go back from right to left, multiply 3 and 1 fourth, you will reach 3 fourths. Why do we do this? Because if we have this expression, it's easier for us to convert, if, to take the value of the simplified 81. I mean, this would become, okay, convert this into radical expression. This is actually 81 raised to the power of 1. Here, this is connected to this. 81 to the power of 1. Okay, let me make it power of 1. 81 to the power of 1, and then you have here the fourth root. And the whole expression now is raised into 3. This is another form of the transformation law. If you have big, very big, or very large radicand, you can do this way. Why? Because actually you can simplify this. Okay, fourth root of 81, you pick any number, a number which will multiply to itself 4 times, will result to 81. That number is actually 3. Okay, 3 times 3 is 9. Times 3, 27. Again, 3 times 3 is 9. Times 3, 27. Times 3, 81. So 81 is a perfect fourth number of what? 3. In this case, the fourth root of 81 is simply 3. Okay, and then 3 cube. Now it's easy to get 3 cube. 3 cube is actually 27. If you have calculators there, I would ask you to simplify this if it's really equal to uh, 27. Sige, I will give you probably amount of time to determine whether they are really equal. Okay? 27 ba yung value ng fourth root of 531,441? Okay, least, or you could do it the reverse way. You can multiply 27 4 times. Let's find out if it's really 531,441. Okay. Okay, for some of you, probably you already did that using your calculators. Yes, the fourth root of 531,441 is actually 27. So this is the discussion for this is, the point for discussing this process is to tell you that if your radicand is very big, you can just simply take out the exponent of the radicand and express it as the exponent of the whole expression. So it's easier to do this. So the answer here is 27. So these are the items found in the practice exercise A of lesson number 2. The only pending here is number 2, huh? This is the only pending here because when we reach unit number 3, this needs to be simplified further. Again, this video contains discussions on the practice exercise A of lesson number 2. The next video will be concerned on the demonstrations on practice exercise B of the same lesson. Use this video as part of your review and practice more and look for other problems to solve. That's all. Goodbye.